I don't work out, Collie. Hello, ladies. How are you doing? All of you are in Korea, right?
Yeah.
Okay. Can I see where you guys are? I'm really curious as to which part of Korea you're in right now.
Like in the countryside.
I know. I saw pictures. I saw video footage that Kurim showed me. It's beautiful outside.
Really? Oh, so you already know what it looks like.
I know, but I haven't seen where everybody else is. I really would like to know. Okay. Well, if everybody's in that's going to be in, I'm going to be talking about alternating current and direct current. If you want to follow along, it's going to be on page 539 of the textbook. Sorry, I couldn't resist. AC/DC is it. Does everybody know what AC/DC is?
No?
You don't know what AC and DC are? Okay, AC and DC are abbreviations. So DC is what we normally have been talking about so far. So far, we've been talking about direct current. Now, direct current is where you're pushing, you're literally forcing all the electrons to move through. Actually, not the electrons. You're forcing the current to move through the circuit. Alternating current, AC is alternating current. And it's widely different. If I was to try and explain how direct current and alternating current work, I would explain it more in that you have, let's have a, ooh, why is that green? I don't want green, let's want black. There we go. Let's just have a baseline of 0 here, and we'll have this as the current. And this axis here can be time. Okay, so can I get you guys to draw? Can I get 2 of you to draw? Can I get Billy and Tim? Can you guys, Billy, can you draw direct current? Like what would direct current look like over time, and what would alternating current look like over time?
I still don't understand this direct current, alternating current thing.
Maybe it's better off if I start off a different way then. So, If I was to grab a bunch of electrons and shove it into a circuit, what would that be?
Zap.
That zap is direct current. When you get zapped from a Van de Graaff ball, that's direct current. The electrons are moving from one place to another. It's one direction.
You got that.
Don't start singing any One Direction songs. If you do, it will fail you. An alternating current, you just had the reference to AC/DC. Yes, the alternating current moves like that. It goes, so the current will move this way, and then it will move back the other way. And then it'll move back this way, and then it'll move back the other way. Did you catch that?
So alternating current is in different directions.
Yep. Yep. Okay. So I
Different
think, yes, it moves back and forth. So let's just say I have, I'm trying to think of an example to be able to show you how this would work. So if I have a light globe, and this will work. Okay, I have an old school light globe. The current goes in here, it goes up this thing, and then you have a little spot there. Okay, so the wire goes through. This here area in here is a vacuum, and if you put the current through, this lights up. Do you remember why it would light up?
Electrons.
What happens to the electrons? How do electrons move through a conductor? Metallic conductor, I should say.
So basically, wait, does it have to do something with protons and neutrons?
No, it has to do with only, it might have to do with proton, atoms, yes, it might have something to do with it.
Didn't you tell us like with the batteries and then the neutrons go one side and protons go one side? And
No. Let's just look at there's electrons going in here. Okay, you've got a bunch of electrons going in here. And when they move through a wire, what happens?
They bump into atoms.
Yes, they
yes.
certainly do bump into atoms. What happens when they bump?
Zap.
They don't zap. Think of the electrical charge as the thing that's moving stuff. Remember when you saw the person with the lightning patterns on them? What's it called?
Lichtenberg figures.
Lichtenberg figures. You had those patterns happening on. What's happened inside their cells?
Zap.
When the electrons move through, what do they do to the cells? What happens when they hit?
Cook.
It releases energy.
Yes. Cooks.
Okay. So when you have part of here and you have, oh goodness, can I do this? Okay, you have part of this wire. Now this wire is made up of molecules elements packed together, atoms packed together. When you have your little electrons, trying to go through here,
What is
they're
that?
not. When the electrons try to go through here, they're going to bump.
What's the big thing?
What?
The big circles.
They're atoms.
It's like
Okay.
Okay. So this would be so normally inside a filament you would have a tungsten filament. So that's a metal. Now this tungsten filament will. Oh goodness gracious me! Why are you being such a pain in the blot? The technical Australian term. So when the electron goes in through the thing, it'll bump around. It's trying to get forward, but it keeps bumping its way through these atoms. Now, when you bump them like that, it releases the energy, and you get light and you get heat. What happens if it goes back the other way?
Is that even possible?
If you've got the electron coming from this way and it bumps around all through these atoms and gets out the other side, it's left additional heat. It's caused these things to release heat and light.
Yes.
Okay. What if I was to switch the circuit around the other way and I was to get the the electron to come in from the other direction, bump, 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 before it comes out? What happens?
It still releases heat.
It still releases that heat and light, etc. So this is what alternating current takes advantage of. You can move the electrons back and forth really, really fast. So at some stage in a DC current will have a set amount of push, and it will always go in one direction. But for an alternating current,
One
you
direction.
actually will have a sine wave or a cosine wave.
A what?
A sine wave.
Yes. So let's just say that at here you have 240 volts, and here you have negative 240 volts.
You can have negative voltage.
Yes, because it's a directional thing.
What? Wait, how does it have direction?
Because your potential energy it's potential energy, correct? It's part of that calculation of potential energy. It depends on whether you want things to go together or go away from each other, right?
Mm-hmm.
So you can determine which direction it goes. So voltage has a direction. Normally, when you talk about voltage, you're talking about absolute amounts. So what you have is at this point here, you've got the electron moving as fast as it can in a full current going that way. And then when you have it at the bottom there, it's going full speed in the opposite direction. So just going back and forth and 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 back and forth. And guess what? The tungsten will heat up and emit light. It goes back and forth. I think the frequency in the United States is 60 cycles a second. So look on page 539. They will ask this. In the US, the alternating current, how do I move this around so I can edit the picture? In the US, your alternating current, where do I select? Get rid of this, you don't need that. Get rid of you, and I'll get rid of you. Go away. Okay. In the US, the AC current, alternating current is 110 volts.
Ooh. That's a lot of volts.
Yeah, but it's the root mean squared. At 60 hertz. Anybody remember what 60 hertz is?
In volts?
No. Do you remember from when we did waves, what 60 hertz mean?
We forgot.
Pardon?
Hey, hold up.
Oh, it goes there and back 60 times a second?
Yes. So it will go forward and back 60 times a second. So if I was to have a point here, if I was to say in 1 second, how many times does this electron go through the tungsten?
$60.
No. It does 60 cycles. How many times does it go through the tungsten wire? Remember, this is one cycle. Okay. It cycles that many. It goes through 60 cycles in a second. It goes through 60 cycles in a second. So how many times does it go through? How many times does it go through the tungsten wire?
120.
120. Thank you. It's
So take my
120.
answer.
Of course.
What do you mean? Of course?
You were very generous in letting the lady go first. So one
Yes,
cycle
of
it will go
course.
this way and it will go back, and then it will go this way and go back 2 cycles, etc., until you get to 60 cycles. 60 times back and forth, which would be 120 times through the wire itself. I think that's actually one. I think that's actually one of your questions. Okay. What's the voltage in Indonesia? You can use the internet. What's the voltage in Indonesia?
220.
Pardon?
220.
320?
220.
I thought it was 240. Normally,
What?
I thought it was 240. I could be wrong. Yeah. So voltage is actually not entirely stable in Indo. The AC is 220 to 240. What's the cycles? How many hertz? How many hertz would it be?
It hurts a lot.
50? I think it's about 50 as well. I think it'd be about 50 as well. Wait, come on. Select, and there you go. All right. So if you get questions on the test that have to do with voltage, that's what you're looking at there. Okay.
Do we use the Indo or?
You can use 220 for Indo most of the time. It will actually tell you for the US one. The book is done for US people, so it will ask the question that way. I want to get rid of this picture. Actually, I will save this picture first, and then I will keep going. Okay. So we now have an AC and a DC definition. I won't go into AC generation at the moment. I don't think that's necessary right now. What I do want you to know next is, how do you turn alternating current into direct current? Because most of your electronic devices will have something like that. Can you read that out for me?
A 100 to 240 volts.
Yes. And what's the DC output?
19 volts.
19? You're kidding. Oh yeah, it's 19 volts DC output. Where is it? There you go. 19 volts at 6.32 amperes.
Yes.
What?
Okay.
What is this?
Sure, Andrew. Not
So-
all appliances have this much information.
I understand, but
Most of them do.
But what you should be really interested in is that this will turn, that thing will turn AC current into DC current.
Let's see, what's mine? It is 100 to 240 volts, 50 to 60 hertz. What is max 1.7A with an output of 12 volts?
Can we get back to the system where you have it on your
I do.
Okay. So there are two things that you want to look at, two devices, two pieces of electrical equipment that turn AC into DC. So the first one is a diode. Now, a diode only allows current in one direction. Will that do anything to DC current?
Make it go in one direction?
If it's going the same direction as the diode, will the signal get through? Will the current get through?
Yes.
If it's going in the opposite direction, does the current get through?
No.
That's what a diode does. Diodes let a voltage go in one direction. It's like a one-way valve. You know what a one-way valve is, right?
Yes.
It'd be like if you had a lever inside the hinge on your door, you can open a door in one direction. If you have a door, you know those movies where you have the doors to the bathroom and somebody fills up the bathroom?
What do you mean?
The door is always opens out away from the bathroom, so the person opens it and the water comes out. If the door opened in the other direction, would you ever be able to get the water out?
Not really.
That's a one-way valve. So what is interesting is if you start adding a diode to if you add a diode to an AC current, still blue. If you add a diode to an AC current, what you should find is that over time, I'm going to get rid of the time bit there because we don't really need it. I want to go back to blue, and I want to go there. So what you will find is when you have, why can't I draw it? When you have a diode in there, and the diode is going a certain way, what it will do is it will get rid of one half of the signal.
Like just randomly puff?
No. So if I have a diode, if the AC current is going like this and I add a diode in there, if the diode's in there, what will happen is for this whole region, you're only going to be having it go in one direction. So if the current can flow, let's say that let's say this current is flowing from left to right. And this current here is flowing right to left. Okay? So you've got the cable, the current's flowing one direction, then the other direction, this direction, then the other direction. If you have a diode, it's like having that door there. The water pushes against it, it won't, if the door opens this way, the water pushes against it, it will open. If the water pushes this way, the door doesn't let anything through. So that's what a diode does. So if it only lets it through in one direction, it will actually get rid of all the current in that direction. So you're left with this, this signal of just a series of positive flows. So the flow will go okay? This causes problems for most electrical devices because it's not stable. What you then want to do is you want to smooth this flow out. Now, the way you do that is you make a capacitor. Do you remember what the Van de Graaff ball did when you let it charge up? If you kept adding charge to it? Could you add charge to a Van de Graaff ball?
Yes.
Okay, so if you keep adding that charge in that one direction, it will also release it when there is no charge. There is a limit to how much you can charge it up, right? Before it releases.
Yeah.
Okay, so if you do that, what happens is you don't let this charge up the full amount when it starts. So as it charges up, it'll be charging the diode as well. And then after it releases, you'll get this sort of, yes, you'll get a much smoother sort of shape. So what happens is, and you can see this on page 540. Page 540 has better pictures. Okay. It should get something like, can you see that? No. Can you see my video share? Not the screen. You can see that. That page 540 stuff is what I'm trying to show you here.
Okay.
So the first thing is you have the diode that only allows current in one direction. And the second thing you add to the circuit is you add a capacitor. Now, a capacitor is basically just a mini Van de Graaff generator. You can add it to a Van de Graaff ball, not the generator. You can stores charge. Okay, and now okay. All right. Can I get you to write out what the effect of a diode is and what the effect of a capacitor is? Can I get, let me just randomly pick someone. GA and Elsa. GA, can you tell me what the effect of a diode is on changing alternating current into direct current?
Um,
Okay. I need a bit more than GA. You can write on the screen if you want, or you could write it in the, here we go. It's in the comments. No, it's not in the comments yet.
I don't know.
Okay. Do you have the textbook with you, GA?
Yes.
You have the textbook? Could you turn to page 540?
Yes.
Okay. Can you see that there is a word in bold? It is the word diode.
Yes.
Okay. And out loud it says, it uses a diode, a tiny electronic device that acts as a one-way valve to allow electron flow in only one direction. Since alternating current vibrates in two directions, you can finish reading it. That's the answer.
Okay.
Okay. You
Yeah.
got it? Okay.
Yeah.
What is the effect of putting a diode onto an AC current?
Patience.
That's all right. I'm patient. I can be patient. No, I can't. I can't be patient. What does it do, GA? What does the diode do to AC current when you're converting AC to DC?
Mm, only half of each cycle will pass through a diode.
Yes. So if you turn it from the passive to the active voice, it just changes it from it only allows half the AC cycle to pass in one direction. Excellent. I'm going to leave it at that for you. Well done, GA. Elsa, what does a capacitor do?
A capacitor helps smooth the bumps.
A capacitor helps to smooth the bumps. Stores charge, so a capacitor helps smooth the bumps.
It produces a retarding effect.
Yep. Yep. It slows how much it goes up, how quickly it goes up, and it also slows how quickly it goes down. It's like that tank of water. If you pour the water in and you stop pouring the water, pour the water in, stop pouring the water, what comes out is still a smooth amount of current. Okay, great. Now, in practice, they don't quite do it like this. They use a pair of diodes. And what happens is you get a series of bumps like this. And then when you put the capacitor in, it kind of smooths that out. It kind of smooths that out almost to be similar to the DC current. So it should look similar to a DC output, so much so that you can use AC power to power most DC devices if you have the correct converter. So this is what your power converters on your laptops and on your phones do. They turn that AC current that comes from the power source into DC. Question. I'm going to hold this up here, and I've got this that tells me what my amperes are as well. Can somebody write down on screen where that horrible red scribble is? Can someone get rid of that red scribble? Yeah, dumb. Can you get rid of that red scribble? And can you write out? Whoops. Can you write out the AC voltage in amperes? And Karina, can you write out the DC voltage in amperes, please? Too many parts here to move. Where is that? There you go. Chat. GC. No, DC. Yes, you want to look at the direct current. Hey, yeah, Dom. Are you there?
Yeah, I'm there.
Okay. Can you read what is the voltage here in AC?
Is AC the top one or the bottom one?
Top one.
Yeah, 100 to 240 voltage.
Okay, so let's just pick the one in Indonesia right now is running at 240.
Yeah.
Okay, so write down 240, and your amperes are 2.
And then what?
240 and the
Now
amperes.
write it on the board.
Yes. 240 with the amperes of 2.
Oh wait, can you guys see me doing something on the board or no?
No.
We can. If you
Oh.
draw on the board, we see it.
Okay, you cannot see that one. No wonder.
Why not?
I don't know. I did something and you guys couldn't see it, so let me try again.
Calm down.
240. Can you see that?
Yes.
Yes. Big and clear.
Okay.
Yeah, don't forget 2 amperes.
What's the amperes?
2.
Sorry, the screen is small for you.
2.0.
Okay. Karina, can you write the next bit?
I don't know.
It's the output.
Okay, you see
Oh, okay.
this number here?
Yeah,
What's that?
19
19 what?
volts,
Correct. What's this one?
6.32 amperes.
Great. Okay, can you write those two on the board, please?
Why do we need to know this?
Because this is how you work out electrical power. I want to look at the efficiency of this device. Great. Excellent. Let's just go with 6. That'll be close enough. All right. So you want to make sure that you always include your units. All right. So we have the AC. We have the AC current coming in here, and we have the DC output. Okay. Please, this is just going to be a simple piece of information. Flip over to page 543.
I have a question.
Just a minute.
It doesn't take long, I promise.
Okay.
That you're lying.
For DC, the one in the
Yep.
bottom there, is it already using the capacitor?
It would have to have already gone through the diode, and actually it should be a pair of diodes and the capacitor.
Okay.
Electric power is equal to your current multiplied by your voltage. Okay?
Yes.
That's your current multiplied by your voltage. So what is the power? How much power is going into this?
Is the current AC or DC? DC, right?
The current is AC going in and DC going out. Just move that over there. Okay. The current is AC going in and DC going out. What is your electrical power going in? Because it actually tells you. Dylan, I'm asking you, what is electrical power? And Jonathan, I've already got Jonathan do something.
Isn't it? Wait, I want to answer.
Hajin, I'm going to ask you what the DC power output is,
For
but you can tell me what the AC power input is.
So for electric power, for the current, is the current like, you said AC going in and DC going out? What is that supposed to mean?
Dylan. It says multiplied by voltage, right? What's the other number we found that isn't voltage?
It's 2.
Wow, amazing.
Yeah, so the power going in would be 2 times 240, which would equal what?
480.
480 watts.
Electrical power.
Oh, so smart.
No. Literally, it's watts.
It's watts.
Oh, yeah.
The actual
Dylan, it's in
unit
the
is
book.
watts.
That's why he said go to 543.
I am at 503.
Okay, what?
I
am at 503.
am so glad that the Patricks aren't actually in this class right now because I would have so many bad
Sandra,
puns and
this is
jokes about
recorded and
what-
probably gonna be uploaded.
Yes, it is. I'm going to be uploaded very soon. This is actually
Oof.
the end of the class. So what is the power of the DC output?
Are you still asking me?
I am seriously asking you.
Okay.
Actually, no, I'm not. I'm going to
Isn't
be
it
asking
Hajin?
Hajin.
Okay, thank goodness. I mean, I think I know, but I need to look at a calculator.
Yes, I expect you to use a calculator here.
I didn't use the calculator for 240 times 2.
Ah, you're fine. Hajin, you okay?
I don't know how to calculate.
You just multiply one by the other. You multiply 19
by
volts
6.32.
by 6.32.
And then you get voila. Do we round it up?
You can round, if you were to round the 19 to a 20 and you round the 6 to a 6.3 down to a 6, you probably get something close to 20 times 6.
It is.
So what's the answer, Hajin? What? Why does it say go on? Okay, I don't think that was the correct answer. Are you okay, Hajin?
Nope.
Nope, you don't have it.
No, she's not okay.
In the chat. So power equals current multiplied by voltage, which would be, the power would be equal to the current, which is 6.32 amps, multiplied by 19 volts. So the power is equal to what? How many watts? What's 6.32 times 19? Literally, all you need to do is multiply. It's just this. You're just multiplying the voltage by the amperes. That's all you're doing to get the power. Excellent. That's, I'm not sure how exact that is, but it should be close enough. So how much power am I losing? How efficient is this?
Not very.
It is super, super inefficient. Would it be more efficient in America?
Yeah. Because it
Why?
uses less volts, but get the same output.
Right. So can you conclude whether or not this particular converter is designed for American use or Indonesian use?
American use.
That's probably the way to go.
I mean, both can be used, but probably America's better.
Right. I find that this particular power converter, this one has been a big pain in the neck to me because it runs super hot. It's that extra power has to go somewhere and it's being turned into heat.
Oof.
So, okay. So, does that help you figure out, would that help you figure out how your appliances will work?
Yeah, but I wonder, like, how do we just kind of estimate, sort of, for some of them?
You can sort of estimate. If you do end up going online, for example, if you go online and you want to look up what watts your refrigerator is or how many watts your microwave is, that works. Some things will tell you how many amps they run on, but the voltage will be supplied by the main, so the voltage should be the same for everything. The amount of amps that something draws and the amount of watts that it uses. These will be sometimes they'll give it to you, sometimes you have to work it out. So if you get given amps, you can work out watts. If you get given watts, you can work out amps. That should be one of the main things you're doing in this project. Most of the time you get given how many watts your light bulbs are. If you turn over the page to page 544, there's a picture of a light globe here. There's a picture of a light globe here, and this light globe this is an old school light globe. It's a 60-watt light globe because you can read that on the front, and it's supposed to run on 120 volts-ish. So you can then figure out the amps for that. So if amps times voltage equals your watts, how many amps go through this particular thing?
2.
2. So 2 times 120 equals 50. I mean, 2 times 120 equals 60.
Did I say 2?
Yes, you said 2.
No, okay.
Try again.
Sweet.
0.5.
Tim, you're a genius. Excellent. Sorry, I shouldn't say a genius. I don't want to state things that
You're
are
a prodigy.
No.
You can say it, Mr. Andrew.
You pay attention.
Woohoo!
That's a much better compliment. Give me 50. Give me one man who pays attention instead of 50 people who are genius.
Wait, it's you're trying to find the amp, right?
Yes, I just asked what's the amperes.
Is it 120 divided by? Oh, it's 60 divided by 120. Okay.
Right. Okay. That's basically it. I'm just going to go back to the share screen so I can save the whiteboard. I want to save that. Okay. And I'll post that whiteboard along with the video. Okay. We good?
Can I see the whiteboard?
There you go. Actually, there's something missing there. Smooths out the bumps. Boomos, that's not what I want. I want bumps, not boomos. There you go. Right, now I'll save it. Okay. Okay, we good?
Yes.
Okay.
What's the dumps?
I'll see you guys on Wednesday. How's your project going?
Not good.
Yeah.
I didn't even start because I didn't know what to do, but now I do.
Okay. All right.
But Mr. Andrew, this sorry, but this house isn't my house, and I can't be like snooping and like.
What's your electrical bill?
Oh, that's going to be a problem, isn't it, if it's not your house? Whose house is it?
Church house thingy, but I also move in a week to another place,
Wait,
and
me
that place
too.
isn't my house either. And then from there, after like a week or something, I move again.
Ado.
Me
Yeah,
too.
so sorry if my thing is very inaccurate. Yeah, that's yeah.
The thing is, if you do an estimate of how much power your house uses, and you can't check it, cross-check it with a bill, you have no idea if your estimates are close or not.
That's good. Because
That's
you
good.
won't know if we're wrong or right.
Yes.
Oh, this is a
We can't just be like, hey church, how much this house be costing?
yeah.
So then I'll just grade you I just won't grade that part of it. I'll leave you.
You can just grade it as pass.
No, I'll leave you as 20. I'll leave you as 20% short.
What?
No.
That is not.
We'll figure out how to do this. I would really like you to see if you can check if your calculations are correct.
Mr. Hendro, when is it due?
Friday.
Mr. Andrew, can we go?
Oh no.
Yes, if you feel like you're done, go.
Yes, thank you, Mr. Hendro.
Mr. Hendro, for the project, for each like plug, does
Yep.
does it like cost like volts?
What do you mean?
Like for the plugs, or do we only count the electronics we're using?
Oh, no. You're looking for things like light globes. You're
Light
looking for
globes.
light globes, water pumps, fridges, microwaves.
What about my CPU?
Why just think of just the computer as a whole rather than the CPU? Because you're attaching your monitor through the computer
Yes.
as well, aren't you?
Yeah. So I just need to figure out how much the computer uses.
Basically.
I do not know how much the computer uses.
Astaga.
Oh no!
Okay. Are you using a tower or a laptop?
Tower.
Okay. You will have a power pack at the back of your computer. Open up the side. It should tell you what the rating of that power pack is.
Like
If
behind
it-
the monitor?
It's no. The power pack should have a big fan attached to it and two sockets, two electrical power sockets for kettle cords.
Mr.
What
Henry.
about a laptop?
A laptop should have it written on it somewhere.
What are you talking about?
Okay.
What?
There are two kettle cord. Turn on your monitor for a second.
Okay, hold up. I got
Mr. Henry, I'll be moving to a new house soon.
Great.
Mr. Hendro.
Okay, you've got a camera part that you can look at the back part of your tower. Show me
Is
the
it,
back-
is it like this thing?
No, that's your UPS. That's not-
Yes, exactly.
okay, that'll add to the inefficiencies. But go to the back of your tower.
This thing? My CPU?
Yes, that's the tower. Go to the back of the
I can't see what's in the back of my tower, but here it goes.
It's black. I
Yes,
can't
it's-
see anything at all. Okay, I can see. Okay, you're looking through a grill at a fan. Where are the plugs? Point the camera.
plugs.
You're far too close. Point the camera.
Okay, hold up. Let me just move the CPU forward so everybody can see it. Why are they still here? Okay.
Because this is entertainment par excellence.
This is not entertainment. This is cruelty right here. Okay. What's in the back? I don't know too.
Okay, that's your access to your motherboard. Where's your?
Yes.
That's the bit that's your motherboard. That's not what you're looking at. I can't see. You want to be pointing where the power cable goes in. Where does
Like
the
this
power?
one? Wait, I think I see it. Is it this one? Does this look like this?
Everything's just black, mate.
Okay, hold up. Let me be a smart boy and on my flashlights. Let's go.
You're gonna do it by the phone.
Of course I am. Okay. Now it's all set. Boom. Is it in the bottom there?
No. It should be up the top.
Is that the top? Like top here?
Fine. You're too close. Get out. All right. Go down slowly.
Okay.
Oh goodness. What are you doing?
I'm going down, Mr.
Guys,
Henjo.
there's so many cables.
Ow! I got electrocuted.
Yes. I cannot see where it connects to the wall. That's one. That's the one. You see that cable there?
This one.
Yes. That attaches directly into your power pack.
Yes. Now
that
what?
That power pack, somewhere on that power pack, will tell you the wattage.
Okay, what am I supposed to do now?
Turn the computer off, take it apart, and have a look at the wattage.
I don't want to take my computer off. It's such a hassle.
I don't know.
It's
the-
okay.
if you
It's
have
for
a-
my grades.
If you have trouble doing that and you don't want to risk it, find the average power for a computer of yours. Actually, go into your BIOS. Go into your BIOS and look at the power because it should have specs. Your computer should have specs.
Wait, can I just look at this thing?
So go. Oh my goodness! Yes, you can look at that thing.
Okay, you didn't tell me this before.
Is that attached to your computer?
Yes, of course, attached to this black thing. I'm not sure you can see it, but attached to this black thing, which attaches back there. Wait,
Oh,
so
good grief.
it
That is
says
what,
100 to 240.
yeah, so max is 1.7 amps at 240 volts.
Is it backward for you? I can't see it.
Yeah, so 1.7 amps at about 240 volts. You're looking at about 400 watt.
400 watts. Okay, noted.
Okay.
Okay.
Oh, thereabouts. And from
I
those
just need to
400
do this a lot more.
Okay.
Okay.
All right.
I'm gonna grow bald soon. You're gonna see it.
You're special, Dylan. Thank you very much.
Thank you.
Okay. See ya. Bye bye, Tim.